he comes up with a brilliant reimagination of physics, which first does something very important. It explains or fits everything we already knew. You can't go and lose that, right? And then all these puzzles get solved. The first thing that Einstein supposedly did after he developed general relativity was he looked back at this precession of Mercury, this problem that Mercury, its orbit is itself rotating very slowly around the sun, unlike the other planets. And nobody knew why. They thought maybe there was another planet between Mercury and the sun. Einstein
called
chose
Vulcan,
because it would be hot.
called Vulcan. We just invented. We were perfectly happy to say it's Vulcan is there. We can't see it, but it's too close to the sun. It's getting the glare.
This was not unreasonable because when the planet Uranus was not traveling where it was supposed to, they invoked a planet Neptune, which they found right where it was supposed to be. So this is what makes science so much fun and why you can't just play the game like you're studying history and going to predict what's going to happen. Because sometimes the planet misbehaves because there's some stuff out there you missed. And sometimes it misbehaves because we have the wrong understanding of physics. And in that case, Einstein showed that his theory would explain Mercury's precession because Mercury was living so close to the sun, it was in what we call the strong gravity regime, where gravity was operating differently than Newton. So to answer your question, we are collecting these sort of cracks and problems, and sometimes that is the kind of harbinger of some certain sort of new revolutionary thing. Sometimes it's the loose thread on a sweater, you pull it, and sometimes it was just that annoying thread, and that's fine. Or sometimes it unravels the sweater, and it's hard to say.
Right, but we live in a society where we want answers to everything, right? And to the average person, you want an answer. But what this feels like is like you're assembling the universe using like IKEA instructions. And then you look at the manual and it's like, it doesn't look like the manual. And you're like, honey, what's this extra part? I don't know. It's dark energy. And why is there another Allen wrench? Like, and so you literally.
Well, I think what we're saying is, A, we're not done because everything isn't fitting. And B, we have this wealth of new facilities which are now coming online that really should help us answer these questions. We have the Nancy Grace Roman telescope.
So that's specifically tuned for dark energy, is that correct?
It's going to be particularly good with dark energy.
Okay, so it's not just another telescope.
Right.
We got smart people figuring we got this problem. Let's design it
but I'm
to
going to
address
ask
that problem.
What we probably you both consider a stupid question. If we don't know what it is, other than naming it dark energy, how do we know what to build to
That's
look
a great
at
question.
what is?
That's a great. So I was actually on this panel called the Decadal Survey that once every decade recommends what to build next. And this is what we thought about. And we recommended this in 2010. And the reason is because it takes us decades to build these things. So what if the science questions change as you're building or the techniques change? So we designed the telescope to measure the current techniques best that could be done, but also recognize that a telescope that didn't exist was a space-based telescope with a wide field of view. Remember I said earlier in this, you need a wide field of view to observe hundreds of thousands of galaxies, and that operates in the near infrared, which it's very difficult to observe in the near infrared from the ground because the sky is very bright.
Define near infrared.
Near infrared are wavelengths that are redder than red, so longer wavelengths than that.
But it's near. It sits closer to the visible spectrum than the far infrared.
Got it.
So near and far, it's stupid words, but we're stuck with them.
Yeah.
So the whole infrared part of the spectrum sits adjacent to the So it's adjacent to red, orange, yellow, green, blue, violet. So it's adjacent to that. And those wavelengths that are near visible, we call those near, and then far. That's all. It's not deeper than that.
So we both build a telescope. We say, well, today this is what we would want, and we think it'll be great. But also tomorrow, this will be the capability that doesn't exist. So there's a discovery space capability where you say, this has got to show us new things because we've never looked in that window. We've never opened that door. So it has both elements.
Got it.
Very important here because that's why build something that only can see what you're looking for or expect. The breadth of those capabilities, that's what advances the field.
But what has to feel at times overwhelming to you is it's a constant moving target, right? So you've developed this telescope, but as you just mentioned a minute ago, around that, new discoveries are being made, new equations are being calculated, right? So it must be maddening because there's never a firm this is it.
What I find very satisfying, when Neil and I were in graduate school, there were sets of questions about the universe, and those questions have either been answered or have changed to these other ones. So
Exactly. They're not even interesting anymore.
Yeah, the story. I mean, we were all like, how much matter is in the universe, and is it going to recollapse? And that isn't even the right
one of our colleagues
thing to think about anymore.
wrote a book called Just 3 Questions or something, or it was some title such as that. And it was because of that book that I now tell the world when they say, what question do you want to see answered about the universe? And my answer is, it's the question I don't yet know to ask, because there's a vista that will rise up beneath me from research being done now, so that I will then ask a question undreamt of today. That's the question I'm thinking of.
Well, and our field of cosmology, right, used to jokingly be said that we only had 2.5 facts in cosmology. So we have so much more information. It's such a great laboratory. Cosmology used to be considered closer to philosophy than physics, and now
there's hardly any data.
Right. Yeah. We knew the universe was expanding. We knew there was radiation left over from the Big Bang. And we knew the sky was dark at night. That was about it.
There's several people thinking about this tension.
Yes.
You're not the lone wolf in this. So are you converging at any point?
So we have a fleet of new observatories coming online. We have the Nancy Grace Roman telescope built by NASA to launch next year, which will study dark energy. We have the Vera Rubin telescope. She was the discoverer of dark matter, one of them. And that is a massive ground-based telescope that will cover most of the sky every 3 or 4 days.
Yeah, I don't see that one working.
A million supernovae. That one is already working. And
you got to contradict me all the time.
It's already online. It's discovered thousands of asteroids that were not even counted.
Well, no one told me.
We have new CMB experiments, the Simons Observatory. We have LIGO is just still getting up and going and has great capability. We expect new results from Gaia. So there are a lot of facilities that really are well poised to give us answers.
So, but is there like a fight out there? Is there a cage match among you guys?
Right. So I would say 5 or 10 years ago, the folks from the CMB particularly were like, well, you local people are probably wrong because it used to be 50 or 100, and that seems like hard stuff. Okay. And maybe some of us were like, Planck looks really good, but gee, I really would like some confirmation of that. So along came new facilities that allows people to check the work, okay? So from the cosmic microwave background, we've had these great high-resolution CMB experiments like ACT and SPT. One's Princeton mostly, one is more at Chicago. And though they have replicated the cosmic microwave background measurements, actually they've even pushed the Hubble constant lower, not 67, but 66.
Are these observatories in Antarctica?
Yeah, one's at the South Pole.
Right,
that's the South Pole Telescope, and the other one's in the Atacama in Chile.
Okay.
And so you need very little water in the
one of the driest places on Earth, the Atacama Desert. As is Antarctica. It's one of the driest places on Earth.
And then nearby, we have seen the James Webb Space Telescope replicate the measurements, which was absolutely critical. We've seen other techniques developed that have cross-checked the measurements, and I just came back from something called the distance network. So not the distance ladder, but how do we combine all of these different measures simultaneously, taking into account their covariance? And what we've learned is...
Distance network, great name for that, because it all has to work together.
Correct.
Yeah.
It's not just a ladder anymore, but it's like, but what if I have this information and this information? Well, this information was calibrated the same way as this, but it gives me a unique measure to something else.
It reminds me of this stupid comic where the Transcontinental Railroad, and there's the Golden Spike, which is the last spike.
Right.
And the railroads come, and the tracks don't match up.
Well, that is the problem. Hey, they're down there.
I told you we were off.
Right. So we've seen a lot of cross-checking, and this problem is not going away. It's been getting stronger and stronger. So I think we have to think hard about what it means.
Has your position altered at all, or at one point you said, I think the universe is giving us a lesson in cosmic humility. It doesn't seem to be following the manual we had.
Yeah.
We can rule out a measurement error as a cause of the Hubble tension with very high confidence.
Yes.
There's some people out there that would sort of say perhaps not. And then...
Well, are you a groupie? You're quoting him from some other program? We have him here. We would have quote him from wherever he was.
He doesn't know half the time. He doesn't know what he says.
Let me define error. Do you ever watch baseball?
Oh, yeah.
You know baseball? Okay.
Yeah.
So Aaron...
This is America. What do you think you are?
Aaron
there's
baseball,
a quarterback. There's a wide receiver. No. Yeah.
So I like baseball that they define an error as there was something that was supposed to be done. You know, you're supposed to field a ground ball, and you messed up, right? And it didn't happen, and they score that as an error, okay? But, you know, making some extraordinary play like climbing the wall and stealing a home run and not doing that is not an error, right? So in our parlance, I would say we are convinced after 10 years of scrutiny that we're not making an error in the baseball sense, that everybody
in terms of measurements and so forth.
Everybody appears to be following the manual carefully. Everybody appears to be measuring what they said they're measured. The data is public. This is very important. Unlike back in the 50 or 100 days, half the battle was people had their secret photographic plates in their drawer. And so you'd have a battle and you were like...
None of the drawers in the drawer.
Sorry. That isn't where...
You guys are freaks. This guy's walking around with a piece of metal in his pocket. You got stuff in your drawers.
So what's important is all the data that I talk about is in a public archive. So I say this star is this bright. It's right there.
I'm sorry, back up on the 50,
wait,
100...
just be clear. So I can verify that, and I don't have to think that... I don't have to just take his word for it.
No, I understand, but back in the day, what do you mean there were secret... You were not publicly
if you were
revealing?
Hubble, literally the guy, right? You would go to the 100-inch telescope, you put in a photographic plate, you'd take your deep exposure, and it was your plate. You took it home to your laboratory.
There was no internet.
And you told people what it said.
Yes.
But
there were lectures about it and so forth.
But no one else had access to your data.
Right.
Now everything is digital.
Right.
And it's...
The point being, you've got a lot of people cross-checking and checking
and so this has been the democratization of science through these facilities. And so what I will say is, in the past, when errors are made, and errors absolutely happen, the baseball kind of errors, our community is so good at jumping on those, right, that I would say within weeks or months, that is found. When something lasts 10 years, when the data was public, when people could scrutinize it, then those become the things that are real things.
And you want to also watch out for whether there's groupthink.
Yes.
And if multiple teams who are otherwise competitors find agreement in what your measurements are, that's a good place to be.
Like there were two groups in the last couple weeks that were using JWST and this method called tip of the red giant branch. And they got 74 and 75. They're unrelated to the more traditional groups that were working. And so the more you see these groups that are independent...
So the value of the Hubble constant.
Correct.
Yeah,
that's right.
Does the 74, 75 versus vis-a-vis 72, 72, does that trouble you?
No, it's down
enough?
with the 60.
It's close enough.
Right. I mean, look, the full range of measurements people make locally is about 70 to 75. And so that's normal. That's kind of a bell curve distribution. So people, the middle is probably around 73, but some people get 75 and some get 70. But the point is,
and you expect that in any random distribution.
The question is, why is everybody getting something higher than the early universe at 66 or 67? And I don't see how that happens by chance.
There is this theorist, Thomas Burkitt, and sort of has another explanation for all of this. And I wanted to get your thoughts on that.
So he is a theorist. He's not making measurements. And he has had a theory for a long time that when we look out in space, we use this approximation. We say everything is smooth-ish, okay? And we can use Einstein's theory of relativity as though if I have a certain amount of matter, it's kind of uniformly distributed in space. In reality, space is quite chunky.
Bumpy,
and he is
whatever.
saying that the mathematics of calculating Einstein's general relativity through chunky space won't be the same as calculating it through the same amount of matter smoothly distributed. And I know a lot of people disagree with him. He's sort of on an island about this. They're devilishly difficult calculations to do analytically. So people have done it numerically with computers where you just kind of trace a particle and you have it go through all this. And people who do that say they don't get what he gets this way. But I'm open to it. Look, I mean, if things are not fitting, you have to be open to a lot of possibilities.
The more things don't fit and the longer you're in that state, the kind of more, you say, oh, who's got...
What do you got?
Yeah, what do you got?
I mean, like, for example, when we discovered dark energy, there was something called the age crisis, where there were stars that appeared to be older than the age of the universe. And that was a problem. And the solution to it was actually dark energy, because when we said the age of the universe, we were assuming that the expansion had been slowing down the whole time. And so when we said, how long ago was everything on top of everything, we would get a young age for the universe, 10, 12 billion years. Once you realize, oh no, the rate we have right now is a fast rate, that's not the average expansion rate of the universe. Now let's do the proper calculation. It pushed the universe to be older, 13, 14, 15 billion years.
Adam, I don't know if you're a betting man, but what would you bet would be the solution to this?
I wouldn't bet. And the reason is because
that's not fun.
I like to think of myself as part of the crew of umpires in this game, right? So we're calling the balls and strikes. We're saying, oh, this thing's traveling this fast. This is so far away.
You can't fix the game a little bit?
I mean, that would be the problem.
You can't do a little Pete Rose here?
If you're umpire, you can influence
I will
the
say,
game.
this is an unusual game. This is not...
Finger on the scale, as the mafia likes to do.
And so, my bet is that there's something interesting going on. But what it specifically is, I don't know.
Okay.
But it's like we've got two thermometers. You're taking my temperature. One says it's 98.6, and the other says I'm at a boiling point. And you're the doctor going, it could be new physics. I don't know.
I would say
I'm
you're
charge
sick. I'm willing to go and say that. You're sick.
You would be a terrible doctor.
One of the more fascinating dimensions of the moving frontier of science is when you don't have an answer to questions that have been posed, or you have data, you can't make sense out of it based on our understanding of how things should be or even could be. Then you got to scratch your head and say, do I have to give up some prior expectations, some prior assumptions that went into this understanding of the universe because the puzzle pieces don't fit? Until Copernicus, our understanding of the world, the universe, had Earth in the center. And how else do you explain planets going forward and backwards in the night sky? Forward and then retrograde and then forward again? You have epicycles. We got that. We got that explained. And then Copernicus comes along and says, I got a new idea. Earth is not in the middle. That's pretty serious. The sun is in the middle, and Earth is just another planet. And we're all going the same direction around the sun. And you say, okay, the math is a little simpler, but the idea doesn't sit right. The epicycle thing, that kind of matched the data. And so now, what did they do? They said, let's check the model. So they checked the model. And it turns out the planetary orbits were not as precisely predicted as they were for the epicycles. Do we throw away the whole thing because epicycles were giving better predictions than a sun-centered universe? Do we just throw it all away? Or maybe there's adjustment on the edges of this. Maybe the idea that the sun in the middle is what's fundamental. And Copernicus presumed that orbits were perfect circles. Why wouldn't they be? It's the heavens, it's where God is, and a circle is a perfect shape. But they weren't. Discovered by Johannes Kepler 50 years later. He shows that they're ellipses. You keep the sun in the middle, put the planets on elliptical orbits, you perfectly predict and understand the motions of the planets. We're in this interesting precipice in cosmology where, the Big Bang is pretty secure, in spite of what newspaper headlines with clickbait might have been implying over the last couple of years. Big Bang in trouble. I think it's pretty secure. If I'm betting we're going to have the Big Bang throughout this. But we're going to have to understand something else about how we interpret the early universe, how we're understanding the expansion in the modern universe. Is there some missing piece that'll make it all come together? Missing piece of understanding that'll make the puzzle pieces of cosmology come together. In a resurrection of the challenge that confronted Copernicus, we kept the sun in the middle, and we found out what else needed adjustment. And at each turn of those discoveries, we had a deeper understanding of the operations of nature. And that's what makes it all so beautiful. And that is a cosmic perspective. Adam, it's been a delight to have you come through town.
Thank you.
I don't know how often you get through New York. I know there's a lot of good, fertile brain activity in the Baltimore.
My sister lives here.
Shout out to her. There's the excuse.
Shout out to her.
Shout out to your sister. And let that be an excuse we can exploit going forward to get you back here and catch up on whatever's the latest thinking.
Can I have your prize? I want to show it to my son. I'll give it back to you, I promise.
Is he here?
He's under my seat.
Dude, thanks for
Absolutely. This is so
coming
fascinating.
through,
I learned a lot, and it's an honor to meet you. Seriously.
Excellent.
Yeah, great.
All right, this has been Star Talk. Neil deGrasse Tyson here, your personal astro.